Your robot is so unique, it's like nothing else. But at the same time, it's strangely human. Can you take me back to the very beginning? How did you come to this vision?
Our vision for a musculoskeletal clone comes from a deep desire to make an android that can do anything a human can do. So a functional human clone. The two inventions I've wanted my entire life since I was a kid are lifelike androids and vertical takeoff and landing vehicles. I grew up watching Boston Dynamics demo videos and frankly expected to already see these lifelike androids all over the world. That hasn't panned out. Today, we still don't have those science fiction synthetic humans walking the streets. Upon decades later, after the arrival of the first GPT systems, it became apparent to me that deep learning works, that deep learning can be scaled up, and that one could today control a high degree of freedom android with a soft and deformable body, and that's a tractable problem that we could bring such a creation to life.
Why building a full body rather than just focusing on the hand?
Well, the mission of the company is, like I said, to make complete androids. But when we first started the company, we started by focusing on making a durable human-level robotic hand. And within the first 18 months of the company itself, this is something we managed to do and something that I'm very proud of. But the hand is really the most complicated part of the body. It has the most degrees of freedom. It has a lot of multi-articularity, which means many one-to-many and many-to-one joint muscle relationships. You have a single tendon running from the fingertip through the carpal tunnel to a muscle in the forearm. And that single muscle will activate many joints at the same time. And in other parts, you have many muscles acting on the same joint. So those nonlinear relationships complicate the problem of creating a human-level hand. Additionally, you have a lot of these long tendons in the hand that you don't really have in many other parts of the body. So you're kind of puppeteering the joints a lot more. You have to exert so much force in such a small amount of volume, which leads to a lot of parts of the system breaking. So making that durable is also challenging. And as a result, in order to obtain a really good human-level hand, we've had to develop very general design systems, like constructing a joint from an artificial ligament or making the muscle monolithic with a tendon. And these kinds of design systems and polymer-based analogs for organic soft tissue elements in the human body are what allowed us to go from the hand to the full body biomechanics, like this protoclone here, in just about a year. So in that time that we went from the hand to the full body, this was a far more fruitful effort for us as a company to continue to keep all of our technology in-house, continue to verticalize and make this entire product. And rather than spending all that time retrofitting with industrial 6-axis arms or something like that, where in doing so we're distracting ourselves from our vision, our mission, and diluting in a way the quality of our product and the uniqueness of our product that involves our artificial muscle technology.
And can you take me to the beginning of the protoclone?
Yeah, the founding insight of Clone is that with an artificial muscle technology that approaches human skeletal muscle in performance, one can actuate natural human skeletons and create truly human-level androids by capabilities, by strength, speed, range of motion, dexterity, and of course intelligence. In other words, if you have an artificial muscle technology that contracts with the displacement of human skeletal muscle, then the resulting anatomically accurate android will have human-level range of motion. Similarly, if the artificial muscle contracts with the pulling force of human skeletal muscle, then the resulting anatomically accurate android has human-level strength, and the same goes for contraction speed and obtaining human-level speed at the joints. So this is the insight that's powered the company to date. And has simplified our design process to something that more resembles just referencing anatomy textbooks and copying things one-to-one than sort of engineering individual actuators at every joint from scratch. And obviously, we're aiming for quite a high bar in a human-level android. Humans are very powerful and can do so much and have such incredible capabilities. So nailing all of those goals that are involved in creating a human-level android in a single morphology is very challenging, and the musculoskeletal design philosophy is what enables this.
Why to copy nature so literally? Because the human body is beautiful, but at the same time it has limitations.
Mm-hmm. At Clone, again, it's this really high bar to clear. The robot has to be has to have strength, serious strength in the fingers, for example. Even an adult female like yourself has very strong fingers and capable of manipulating a knife to cut like a pineapple or a watermelon, or to lift a heavy cast iron pan, or to open a heavy office door. So strength in a human being is a very tough thing to nail, and is something that motor actuated humanoids today still struggle with. Getting to human level speed is similarly challenging, especially to do at the same time as achieving human level strength. And then obtaining a soft and fleshy body, a lifelike appearance. Bonuses, these are also part of achieving parity with the human being. Aiming for so many things at the same time while still trying to keep the cost low, still have a design that's producible, is just a really tough challenge to nail when you have to go through with intelligent design of every piece of the system. And start with a rigid exoskeletal shell of a human, and then try to shoehorn as many motors and batteries inside of that volume as possible. By contrast, we can actually distill the number of problems we have to solve by copying nature. With our musculoskeletal design philosophy, we can just focus on making an artificial muscle that works, finding polymer-based analogs to various soft tissue elements inside of the robot, and then consequently just copy anatomy textbooks and reference anatomy textbooks one-to-one, and not have to do nearly as much engineering design.
Are you mostly copying human body, or are you bringing in any improvements?
Right now, at least when it comes to the body, we just want to get to human parity. This is a pretty challenging thing in and of itself. So just getting to human level range of motion and strength and speed is already quite a challenge. This is something that I'd argue nobody has done today yet successfully. I'd also say Clone is on the verge of being able to achieve this, given that we tackled already the hardest part of the body in the hand. So just getting there is already pretty tough. That's what we're aiming for. If you have a human level body and a super intelligence in the brain, then you will have an android that is capable of doing anything humans can do, and probably more. But there's something we don't think about often is, should we add a second thumb, or are 3 fingers enough, or are wheels superior to legs? These are kind of intellectual questions that we don't really take the time to think about and answer. With the musculoskeletal design philosophy, we don't need to do that. We just need to get to human parity to get the robot that we really want.
Looking ahead, which applications and which markets you foresee for the robots? Mm-hmm. So which tasks you design it for?
Mm-hmm. I think the clone is the ideal human companion. Your clone is your complement that fits into your life like a perfect jigsaw puzzle piece. So you wake up in the morning and your clone is at your bedside with a tray and breakfast bites and an orange juice. Before you get into the shower, your towel is already waiting for you. When you get out of the shower, your dirty clothes have already been moved from the floor to the laundry basket, and your clean clothes, your attire for the day is laid out on your bed for you. As you head out of your house, your android is following behind you, holding an umbrella over your head if it's a rainy day. And you get to your workplace and your android is acting as your assistant, helping you make your job super easy, whatever your job may be. This is sort of the android companion lifestyle we envision at Clone, really transforming every aspect of your life, being as sort of attached to you as your iPhone is today.
What is your expectation regarding the battery life?
Battery is sort of this, there are a lot of variables to that equation, obviously. Every design decision we make, over the years all stacks up to the battery life at the end of the day. But it's mostly a function of the efficiency of the robot in combination with the energy density of the robot. So total energy in the robot times how efficient the actuation and power drawing parts of the system are. With our first prototypes, should be able to get an hour of running life, meaning we should be able to get an hour of operation where the android is sprinting at full speed before it sort of drops from a dead battery. And we anticipate to push that number a lot further over the years with some innovations that can't talk about just yet, but we should be able to get this to at least a few hours, which is something that I argue is pretty tough for most humans, including myself. I don't think I can run straight for 3 hours straight, without needing to refuel. So that's just again, use running as kind of a measurement here, because it's quite easy to compare, let's just say, across maybe other robots as well, like just how long can the robot run? What's the distance a robot can travel on its feet before it drops? But in more practical application, for example, in a robot in a home, it's not doing backflips all the time, it's not sprinting all the time. And the android is going to be consuming basically as much power as its muscles require to perform various manipulation tasks rather than really power draining locomotion. So I'd expect even in our first robots that we make, that 1 hour of running life should translate into several hours of operating life for manipulation in the home, for example. It's hard to say exactly though, because it's just, there's so many variables involved, like the type of task that it's doing. So can't really say until we actually put the robot to the test, manipulating objects like all day.
When it comes to communication with it, you expect just naturally talking to him and giving him a task, or how do you envision it working?
There's both verbal and nonverbal communication. So with a good enough memory, a robot that has been tasked with certain activities kind of day over day, you can expect that it should kind of be able to anticipate the sort of tasks that it needs to be performing day over day. But of course, that's pretty far abstracted away at first. We're talking about, in our first fleets at least, users demonstrating to the robots how to perform new skills that we haven't already trained it to perform. And that'll involve largely a robot, for example, standing behind you, watching you perform a task with your own two hands, and then being able to take that data point and with the action labels of what exactly you did with your own hands, and then learning over that data. After that, of course, though, there's a layer of abstraction with the vision language action model, or your frontier LLM, that allows you to be able to language command the robot. In other words, in addition to having action labels for task demonstration, you also have a language label that's describing what the robot's doing in that task. And with a large enough, very labeled data set of language labeled robot actions in the real world, one should be able to language command the robot. So just tell it what to do. And it's really after that where you get to the point where the robot can start doing things autonomously, already anticipating what you want, and things like this.
When it comes to technology, it looks very complex. So how did you make this choice for synthetic muscles over motors?
On a design level, motors are constantly a trade-off between force, speed, power consumption. Motors, again, require to use motors and to make a humanoid robot. It requires this intelligent design of starting with this exoskeletal rigid metal shape of a human being, and then trying to stuff as many motors and batteries inside as you can, with the hope that you can in fact fit enough actuation and battery to replicate every degree of freedom of the robot. And by contrast with artificial muscles, we just have this existence proof that if the muscles are comparable or getting close to parity with human skeletal muscle, that the resulting robot will have all of these specs hit, all these performance specs that a customer might want hit. To get to human level. And sort of additionally, on the manufacturing side of things, motors are relatively complicated to manufacture. They require expensive CNC machines, like assembly lines, precision manufacturing gear trains, and things like this. Whereas we have technology that automatically produces muscle fiber by the kilometer, after which we're just cutting and pasting them at the bones to the right length and then attaching them to the bones. So on a manufacturing level, it's actually quite a bit easier to do things our way as well. But again, ultimately, it just comes down to where you want to go. So if what you're interested in is to make a robot that's sort of good enough to do, an enumerated set of 10 or 20 tasks, you can then start from there and, intelligently design a motor-actuated humanoid or non-humanoid that's sufficient to achieve that goal. Where you want to go is to make a human-level android that can do anything a human could do and never get bottlenecked by too heavy an office door or too dirty a cooking dish, with really crusty food that needs to be scrubbed off with a lot of force. And you just don't want any kind of edge cases in a human environment, and a robot that's able to transcend all of that. Then it really helps to have an existence proof and a certainty that the design you're pursuing does end up at that end state, given a small number of technical problems are solved, such as having an artificial muscle that has a really great contraction force, having a monolithic musculotendon, so tendons don't break, joints constructed with ligaments, and so on. So just a small number of problems solved with really great general design systems are sort of enough to give us this guarantee that the resulting robot that will end up making will have all these human-level capabilities.
Cool. And as I understood, you special material for the muscles. Do you manufacture it yourself?
Yeah, I can't go into the details of all the manufacturing of the muscles, but the artificial muscle is a fluidic muscle. So it's pressurized with a fluid, either a gas or a liquid. Either will work, but will have slightly different dynamics in the muscle behavior. It's basically based on a muscle called the McKibben muscle, So you have an inner rubber tube, and when it's pressurized with fluid, like a balloon, it expands radially. And when surrounded with a inextensible textile braided sleeve with sort of these scissor linkages, you're able to constrain that radial expansion of the balloon to produce a linear contraction with a pulling force in a single axis. You get to mimic a lot of the properties of human skeletal muscle this way. And then all you have to do is just attach it to the right points on the bone to pull the bone at the angle at which you want to for that degree of freedom or that movement.
So as I understood, it's a hybrid system which uses air and water.
No, actually. A fluidic muscle can use either. We have made prototype robots that sometimes use air, largely because you can have a central compressor that, for example, powers this facility, powers a lot of the cleaning tools in our facility here, and we can quickly hook up little robot prototypes to that central pressure source and rapidly actuate them, check the range of motion, see how things are working, throw it out, and move on to the next one. So for that prototyping phase, working with air is quite helpful. Toward our vision of an untethered bipedal android, that doesn't have any cable to the grid or tube to a central pressure source, we necessarily have to use a compact hydraulic pump that fits inside of this rib cage and abdomen skeletal torso volume. So fitting a pressure source in there requires us to move from air to water. And so the product that eventually will make its way to the market will be a hydraulic android that uses water as the fluid to pressurize the muscles.
It's interesting because also from the maintenance perspective, so how do you fill in water when it evaporates, for example? Does he just drink?
Yeah, well, the water is largely staying in the system. If there's some reason to flush the water out, then yeah, it could flush it out with a natural human organ and then drink more water as well, or something like this. But mostly the water is just staying in the system, and when it bleeds out of the muscles, it goes back into a reservoir, like just some kind of container for excess fluid that's not needed when all the muscles are relaxed.
It uses some sort of a pump, right? Mm-hmm. Can we say that this pump is a sort of a heart?
Yes. The robot's pump is essentially a hydraulic heart. So in the human body, the human heart is pumping blood in order to chemically activate muscle fibers. So it's transporting blood to all the muscles in the body and chemically activates fibers with ATP, or essentially fuel. In a clone, the blood is not really the same thing. Here, we're actually using fluid to pressurize the muscle for hydraulic force transmission. So the fluid itself is what's turning into a rock essentially when it hits the muscle, and we obtain a full muscle contraction. So the amount of power required by our hydraulic heart is quite a bit more than the amount of power required in the human heart, where blood pressure is quite low. So this is a very high BP robot.
How do you address the challenge of robot stability? Is it the same way how our human body does it?
By stability, do you mean like
bipedal stability?
Bipedal stability. Robust locomotion for robotics, for like bipedal humanoids in general, today requires a physics simulator. So generally, the way it's done is you're procedurally generating terrains in the simulator, a beach, rocky terrain, grass, and so forth, and you are training your running gait or walking gait or whatever locomotion behavior that you're trying to train across all of those terrains, of course, with randomized parameters, physical parameters like different gravity and friction and center of mass and things like this as well. And then you're taking that policy and you're trying to transfer it to the real robot. And so a lot of the work that goes into robust locomotion today is largely about really good infrastructure for this sim-to-real problem that allows a robotics company to bridge that domain gap between the simulator and the real robot very quickly. In one of these motor-actuated humanoid robots that have a rigid body, it's relatively straightforward to simulate in a GPU-accelerated physics simulator. It's largely just a bunch of cylinders and chain links and things like this. Whereas in the musculoskeletal clone, we have these artificial muscle fibers with very specific type of dynamics, and we have a lot of non-cylinder-like components in the robot, and features and things that need to be simulated with very high fidelity in the GPU-accelerated physics sim. So this is sort of the bottleneck for the company to get to very robust locomotion. It's just getting a faithful clone of the clone in the simulator, so that we can randomize domain parameters and procedurally generate terrains and worlds eventually, and learn various gates from there.
On the intelligence side, which chips, which hardware are you using to power the protocol?
We'll use the NVIDIA Jetson in the brain. This one's got a Jetson in the skull. If we can get 2 in there, we'll use 2. One for probably planning, one for motion control. But yeah, today it's just the NVIDIA Jetson chip that controls the entire robot. And I imagine over the longer term, as we continue to freeze various elements of the robot, including tactile sensing and closed loop control for the hydraulic pump, this hydraulic heart, we'll end up using ASICs across the body, kind of like in the human body where you have neurons near the heart, you have neurons at the wrists, and I expect that in the long run we may end up adding ASICs in various parts of the body.
How about sensors? There are so many sensors in our body. Which ones you decided to include in your robot?
Yeah, well, a fully observable system is the best way to go to make a really easy to control robot. So obviously you would want, ideally, joint level position sensing, so the position of all the joints. You'd ideally want the torques at all the joints, so the forces of rotational forces at all the joints. And then on the muscle level, ideally you would want the muscle position, so the length of the muscle contraction, as well as the force, the pulling force on the muscle. And then on top of those 4 pieces, you'd also want some kind of tactile sensing with the environment. And vision and audio is kind of obvious. Out of those 5, we're nailing almost all of them. We've delayed tactile skin a little while longer, since the dominant paradigm for controlling robots today is position control. In other words, just like retargeting the position of the joints and kind of ignoring the force feedback from the environment. But in the long run, I imagine that this tactile feedback will, especially if it's from a very whole hand skin with very high resolution sensing that effectively produces force maps from the hands that function like images, that it will be very, very useful to the robot foundation model to perform all kinds of manipulation tasks. But for now, to just be able to observe the muscle positions, the joint positions, and the muscle forces, we have enough information to teleoperate the robot, to leverage motion capture data and human video data as well when training a foundation model. So that's kind of the scope of the sensing for our first set of robots.
So basically, you will be training it in a simulation.
Well, that's just for locomotion. So locomotion is this thing where a baby takes quite a long time to walk. So a robot as high dimensional as ours, kind of you really want to leverage the simulator to get whatever evolutionary priors humans come out of the box with when we're born, and to kind of skip that baby learning to walk phase of however long that may take, depending on the learning algorithm. So toward locomotion, walking, running, standing, climbing upstairs, and so forth, the physics simulator is important to leverage. That SimToReal approach likely can also be used for manipulation. The dominant approach for manipulation today, however, is largely just collecting a lot of manipulation data and attempting to train some kind of robot foundation model over that data, whether it's a world model or a VLA model or something else. So that means the manipulation side of things, solving the learning problem for manipulation, is largely a matter of collecting a large and diverse set of interesting and obviously useful bimanual manipulation behaviors. So using tools, a variety of tools, manipulating a variety of objects, performing tasks with the hand that are not, exactly the same. So like there's, for example, a lot of closeness between using a pencil and manipulating a knife. The geometric structure of that kind of manipulation task is quite similar, whereas rotating an object between your fingers like a pen or something is kind of totally different in terms of the information in that task compared to like using a pencil. So collecting a lot of diverse manipulation data that really covers the entire, really as much of the space of possibilities for the manipulator. In our case, these human level robotic hands is sort of the critical factor to training a robot foundation model over that data and really being able to generalize to a new manipulation task that the robot has never seen before. So this is ultimately the direction we'll pursue in the coming years to make our robots general purpose.
What will be the main difference between the current version and the next alpha version, which is coming soon, in terms of capabilities and what it will be able to do?
In terms of aesthetic appearance, you can imagine it's going to have skin. So it will we won't have all these muscles exposed in the robots that we actually end up selling. We've heard some feedback that the robot can look pretty frightening with all these muscles exposed. And I always argue that if you cut open a human under the skin and you expose all of our muscles, it also is quite frightening. So aesthetically, that'll be important to make sure we're not unnerving our customers. By capabilities, we should have a first version of a robot foundation model that's capable of learning to perform new manipulation tasks. That'll be how users end up using their robots. They'll have to show it how to perform some new task, and then the robot, after a handful of demonstrations, should be able to perform it effortlessly. And that capability is something we're not there yet. As we continue to build out our stack kind of layer by layer, from the valve control to the muscle control to the joint control, to eventually the data collection and robot foundation model training.
Why did you decide not to make a human-looking face?
This is something I think we will do, but it's a challenge to make a face that's compelling, that fits the aesthetic of the rest of the robot. So it essentially needs to be a perfect human face with 40 facial muscles, replicating every little micro expression in the human face. And while this is something we could do, it's not essential to deliver the first fleet of clones capable of providing a crazy amount of utility. And it's also one of those problems where it's not really worth it to do in a subpar way. It really needs to be perfect to make sure that we're not ending up in the uncanny valley with an underactuated face or a particularly scary looking face. So this is something that we'll treat really well and make sure we get right before we introduce that likely separate product line to the market.
What is the biggest technical challenge that you are solving right now?
There are quite a few, I'd say, but today the milestone that we're aiming for to, I guess, blow everyone's minds, including ourselves, is getting to the untethered walking biped. So, like, really the first synthetic human that is mobile, walking on its own. It doesn't require any kind of cable to the grid or tube to a central pressure source. That involves not only, obviously the physics simulation and software required to train it to walk, but also requires a ton of compactification and clever arrangement of the valves, batteries, hydraulic power unit, which includes not only the pump, but accumulators, a reservoir, a ton of tubing and cabling, and getting all of that fit inside of the limited volume we have inside of the ribcage, abdomen, and pelvis. So this is largely the focus of the company outside of continuing to improve the biomechanics of the robot.
There is this concept of embodied intelligence. Do you think that the true superintelligence will require the body?
The superintelligence doesn't require a body, but it makes it probably a million times more useful to us. You're almost nerfing your superintelligence if you don't give it a body, because it's just the vast majority of the things that I want to command some intelligent system to do is in the real world, because I'm an embodied being. So to drive utility out of a superintelligence, I'd argue that you really do want it to have a body, and so robotics will end up becoming this great lever for modern deep learning, modern AI. The scarcity for intelligent systems today is very good ground truth data about reality. So if you want an intelligence that's going to continue to get smarter and understand reality better and potentially open up new physics and things like this, that intelligence needs to have a lot of reality data. So you can use synthetic data, it seems nowadays, from the frontier LLM companies to continue to push that forward. But I argue that an increasing amount of data collected in reality by robots that are collecting not only visual data, but tactile data about the environment, that massive visual tactile data set that will come from a robotics company that's capable of scaling up their robots to massive scale will result in very intelligent, a very smart superintelligence, maybe likely a very different kind of intelligence as well, but maybe an even smarter intelligence. I could definitely see a world that goes that way.
Thank you.
Yeah, you got it.